Now we found the reinforcement at the midspan of the slab, and we found the reinforcement at the first interior support, and it was 435 millimeter square per meter and 395 millimeter square per meter. And we have calculated first the depth of the slab, and then we calculate the moment at this negative moment region and at this positive moment region. Based on that moment, we provide this reinforcement. Now we don't know whether this reinforcement provided will satisfy the minimum steel requirement for the AS3600. Now that minimum steel requirements provided in clause 8.1.6.1 on page number 111. Now these minimum steel reinforcement requirement are provided to prevent the sudden failure. So regardless, sometimes your calculations may require that you don't need to provide the reinforcement, but Australian standards maintaining that you must have this minimum reinforcement check. Okay, you must have this minimum reinforcement in your slab. You can't have just a slab without the reinforcement if your bending capacity is just carried by the concrete. So you might end up, well, let's say, use some concrete in a way that you don't need reinforcement, but the standards maintaining that you must have the minimum reinforcement to prevent the sudden failure, because you don't want to collapse that slab if you don't provide the reinforcement. So the minimum reinforcements given in this clause, and someone might say that okay, this is exactly the same in the beam, because this is the beam examples, right? This is the strength for beam in bendings, right? So it's not a slab. Now please note, the one-way slab is actually the beam. It is a 1 meter wide strip, and it's actually the beam that we are talking about. So in that case, if you are beam, so we just going to use this one for one-way slab. Please consider this equation for one-way slab, because one-way slab is classified as a beam because it's just a 1 meter wide beam. That's what's considered. So we can still use these equations for the calculation. So AST should be greater than alpha b. Alpha b is 0.2. I did not write alpha b here. Instead, I just write straight 0.2, and we are working with the rectangular 1 meter wide strip. So if I show it to you in my previous one, we are working with this 1 meter wide strip with the depth of 190 millimeters. So that is rectangular. So we can use 0.2 d over d square FCT f over FSY BW and d. Now in these equations, I think we have all the details except this FCT dot F dash, which is the characteristic strength of the concrete. So if you go to the clause 3.1.13 at the start of the standards, I can take you here. So there you go. In here you have a characteristic flexure tensile strength of the concrete. You have this FCT dot F is equal to 0.6 FC dash. Now in that case, if you have FCT dot F, you will have we have this FCT dot F, which is the 0.6 times FC dash, and if the FC dash is given in the questions 25 megapascal, so the calculations give 3 megapascal. So now we have all the details. We substitute the value. 0.20 depth of the slab 190 millimeters. I think we calculated this in the first 3 videos where we estimated depth of the slab 190 millimeters. I can show it to you here again. That was 190 millimeters that we calculated. Small d effective depth we calculated 159 millimeters square. FCT dot F characteristic strength of the concrete, tensile strength of the concrete, which is 3 megapascal, we just calculated, over yield strength of the Rio is 500 megapascal class N, times the width of the slab. We are assuming 1 meter wide strip for one-way slab, so we're taking 1000 millimeters times d 159 millimeters. We found that effective depth d is basically, we are talking about this 1 meter wide strip. If you have this Rio here, that d is a small d, and that d was 159 millimeters, and this capital DS that we use 190. So capital DS is equal to d is equal to 190 millimeters in those equations. So if you satisfy this one, 272 millimeters square per meter. Now please take a one notes here, that is independent of the slab location. So the AST this AST mean, let me put AST minimum. That AST mean is, if you are looking the slab here or slab here or slab here, anywhere in your structures, this AST mean is independent of. So you don't need to calculate the AST mean here, AST mean here, AST mean here. You should use this AST mean anywhere anywhere on your slab. So we will use this AST mean many times. So we just keep these numbers handy somewhere where we're going to use this AST mean many times. Now let's check it. We calculated this 395 millimeter square per meter in the slab at the tensile at the mid span, making sure that this 395 comply this minimum reinforcement. Yes, 395 is greater than 272, so that is okay. At the interior span, you have 435, which is greater than your AST mean 272 millimeter square per meter, so that is okay again. So I think we will do the check in next video. We going to making sure that once you have AST minimum, in the next video we will going to do the crack control check, the minimum reinforcement requirement for the crack control. So we're making sure that 395 and 435 millimeter square reinforcement area satisfy the crack control requirement. It satisfies the minimum steel reinforcement requirement, but we have one more checks to do in the next video. Thank you.